Hi class, this is Sir Alex Basco and welcome to our lesson in General Chemistry 1. Today we are finishing our discussion in Lesson 4 by discussing Lesson 4.3. Again, this is the last part of our basic knowledge on stoichiometry. This time what we are going to do is deal with empirical and molecular formula. Last time what we've learned is basically how to measure the mass of a compound, and we also learned how to measure the percent composition of each element in a compound given a specific mass or even 1 mole of that compound. So what we are going to learn today is to actually use those previous knowledge to this time create the empirical and molecular formula. So you can think of it as kind of like the other way around. So at the end of today's lesson, what I want everyone be able to do is first be able to calculate the empirical formula from a percent composition of a compound. Again, previously we've discussed how to make the percent composition. One of the easiest example that I had in a previous discussion was the percent composition in 1 mole of NaCl, wherein we can measure that in 1 mole of NaCl there is about 39% sodium and 61% chlorine. And I hope you guys still remember how to do that, but our focus today is this time we are given the percent composition, and what we want to do is use that percent composition to create the empirical formula. It's something that I hope you guys are still familiar with, because we discussed what empirical formulas were when we discussed representing compounds. We're going to do a little review of that empirical formula as we continue on with this lesson. Moreover, what I want everyone be able to do is to calculate the molecular formula given the molar mass and the empirical formula. So this time, not only are we going to create the empirical formula ourselves, but we are also going to identify and create the molecular formula of a compound given its empirical formula and given the molar mass of that compound. So without further ado, let's go ahead straight into our discussion by first discussing or reviewing ourselves what are empirical and molecular formula. So in the end, empirical and molecular formula are basically chemical formulas, and these are important because chemical formula is what we use to actually identify or basically show the composition of a compound. And there's a lot of type of chemical formulas, but more specifically we are going to deal today about empirical formulas, which is the simplest whole number ratio of atoms. This is the smallest possible whole number possible in the subscript of the compound. Next, what we have is molecular formula, which actually shows the actual number of the atoms in the compound. So they're very related. The only difference is empirical formula. This is the simplest, this is the smallest whole number possible. While molecular formula is the actual number of each atoms in a compound. I hope that is clear enough. We've done some examples when we were discussing about representing compounds when we talk about representing compounds. So one of the easiest example is glucose. Glucose is a simple sugar. Its molecular formula is C6H12O6, right? So we have 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. That is the molecular formula. That is the actual whole numbers of each individual elements in the compound. If you want to take the empirical formula, we'll take these subscripts, and what we're going to do is to find the least common denominator, meaning the smallest possible number where we can divide each individual subscript. And the empirical formula happens to be CH2O. So this is the basic, the most simple possible composition of glucose. With just this, there's not a lot of information that you can get as opposed to molecular formula, but each has their own uses. So what we are going to do is we are going to find the empirical formula and molecular formula of a specific compound. In our examples, what we are going to do is to actually find the molecular and the empirical formula of ascorbic acid, or most commonly known as vitamin C. But let's go ahead. How can we find the empirical formula of a compound? What we need is to have the percent composition of the compound that we are looking for. So again, if we want to find the empirical formula, what we need first is the percent composition of a compound. So for example, in your tests, in your homeworks, you would be given a specific percent composition of a compound, and maybe I'll have you guys find the empirical formula of that specific compound. And after having those percent composition, this is usually given in the problem, what you're going to do is first assume that you have 100 grams of that compound. And let's make it easier, and I'll explain later as we go on example why we have to assume 100 grams of that specific compound. Okay, so after assuming you have 100 grams of that compound, you have to find the number of moles per element. So for example, glucose. If I'm looking for the empirical formula of glucose, what I'm going to do is to assume I have 100 grams of glucose. And then what I'm going to do next is find each individual moles of element. So how many moles of carbon do I have? How many moles of hydrogen do I have? And how many moles of oxygen do I have? After that, using the smallest mole, so after finding each individual mole of these elements, or whatever element you have in your compound, you have to divide those moles to the smallest mole that you've found. And after doing that, you're almost basically done. If they're all whole numbers, that's basically your empirical formula. But if there's at least one non-whole number, so they have decimals, what you want to do is to find a multiplier to convert that decimal or non-whole number into a whole number. Sometimes it's impossible to make it a whole number, but make it as close to whole number as possible. So for example, if you have 4.01 or 3.02, then that is fine. That is very close to a whole number. But if possible, if you can find a very specific whole number, then that would be better. So after that, what we're going to do is also find the molecular formula. And if you want to find the molecular formula of a compound, what we want is first we have to know the empirical formula of that compound. And the next important matter that we want to know is the molar mass of that compound. So how are we going to find the molecular formula? First, what you want to do is find the empirical mass of a compound. Empirical mass is basically the total mass of your empirical formula. So you can find that by first looking for the individual mass of your elements in the compound, and that's called the empirical mass of each element. And by adding those individual mass in your empirical formula, you will find the empirical mass of the whole compound. It's basically the thing that we did previously. When we were looking for a mass of a specific compound, we identify what are the atoms, how many atoms of each element we have, and then we find the atomic weight, right? So that's very similar in what you want to do is empirical mass, but instead of using the molecular formula, you are doing it in the empirical formula. And after finding the empirical mass of your compound, what you want to do is use the molar mass of that compound, which the molar mass is what we've been looking for in our previous examples in 4.2. So you want to divide the molar mass by the empirical mass of the compound, and you will be able to get a multiplier x. And after finding that multiplier x, what you want to do is use that multiplier x and multiply it to all the subscripts found in your empirical formula to find the molecular formula of your compound. Okay, so that's a little bit of discussion and what we're going to do today. Let's go ahead straight to the sample problems. So let's begin first by finding the empirical formula, and then our second sample problem would be finding the molecular formula. So let me go ahead and we're going to transfer to the whiteboard. Okay, so this is what we're going to do. We are going to use the whiteboard to solve our sample problem 1. So this is our sample problem 4.3.1. Again, what we're going to do here is find the empirical formula. So what is the empirical formula of ascorbic acid, or commonly known as vitamin C? And they gave us the percent composition of each individual element of ascorbic acid. So ascorbic acid has carbon, has hydrogen, and oxygen. And it has 40% or 40.91% carbon, 4.57% hydrogen, and 54.50% oxygen. So, like I mentioned earlier, we can find the empirical formula of a compound. This is our compound, ascorbic acid, by first identifying the percent composition. And since we know the percent composition, let's go ahead and solve for the empirical formula. Okay, so let me go ahead. What I'm going to do first is I'm going to write my given. So what were given to me in this sample problem. So the first thing that was given to me is the percent composition of each individual element, wherein I have percent of carbon, which is equals to 40.91%, and they also gave me the percent of hydrogen, which is equals to 4.57%, and lastly they also gave me the percent of oxygen, which is 54.50%. So after that, the next thing that you want to do is to assume that you have 100 grams of vitamin C. So why is this important? Why is this 100 grams important, right? So I mentioned earlier that I'll explain why. Well, before I go there, let's go ahead and finish some of our important information. So we have our given. Next, what we want to do is identify what is being asked. So here, what is being asked is basically the empirical formula of ascorbic acid or vitamin C. Now let's go ahead on to the solution. So again, let's go back to the question. Why is it important to have 100 grams of vitamin C? Well, if you assume you have 100 grams of vitamin C, then if you remember what percent composition is, percent composition basically tells you how many percent of a atom or a molecule you have in a specific compound based on their masses. So in NaCl, we were able to get 39% and 61% because we based our information to the grams. So if you guys remember, NaCl itself has about, I believe, 58 grams, remember? And when we divide it, we remember that Na has about 20 something. Sorry, I forgot. Or 25, I believe. Yeah, something about 25. And Cl has about 33 grams per something. This is just approximate. This one are very specific. I can't remember the specific atomic weight of each. So what we did is we assumed this to be the 100%. And what we know now is by doing that, we can actually find, by basically dividing this number divided by the total mass, by dividing the total mass of our NaCl dividing the mass of sodium from NaCl, we can find this 25, how many percent of 25 grams is from 58 grams. And we found that is about 39%, and this Cl is about 61%, if I'm not mistaken. Yeah, so that's what I remember. I may be wrong, but it's something like that. So we assume this to be 100%. So here what we're going to do is we're going to assume we have 100 grams of vitamin C. If we do that, that means basically these individual percent here should be about 100%. So if these are all 100%, so 100 grams is 100%. I hope you're seeing that. If you have 100 grams of vitamin C, meaning 40.91% of carbon from that 100 grams is basically 40.91 grams of carbon, which means you also have 4.57 grams of hydrogen, and it means you have 54.50 grams of oxygen. So it's quite easy now, since you have 100 grams of vitamin C and this 100 grams is equals to 100%. Therefore, these percentage right here of each individual element in your vitamin C can be basically their weight. So that you found the weight, now this is the weight of each individual atoms you have in your compound. What you want to do is find how many moles you have. So after doing this, you assume 100 grams. What you're going to do next, maybe let's use numbers instead. So this is the first thing you want to do is assume you have 100 grams. Next, what you want to do is to find the moles of each individual atoms. So let's look for the moles of carbon first. So the moles of carbon can be found by basically moles of carbon, taking how many, 1 mole of your vitamin C, so that's 1 mole, or sorry, by basically taking the atomic molar mass. Do you guys remember the molar mass of carbon? This is the atomic number that is found on your table of elements, and then just divide it by moles. So you have, if you have 40.91 grams of carbon, and then the molar mass of carbon is actually about 12.01 grams per mole. Again, you will find this at the bottom number of each element in your periodic table. So we've used this a lot. We've been using this a lot. So after, if you do that, you can actually find how many moles of carbon there is in 40.91 grams, because 12.01 grams is equivalent to 1 mole of carbon. So if you have 40.91 grams of carbon, then how many moles is that? So you can just find that by basically dividing, because the grams gets cancelled and the mole becomes basically kind of like inverse. So this will become mole per gram, the grams gets cancelled, and you were left with 3.41 moles. What that means is 40.91 grams of carbon is equivalent to 3.41 moles. And you want to do that in each individual element. So let's find the mole of hydrogen. So we have 4.57 grams of hydrogen, and the molar mass of hydrogen is 1.008, I believe, grams per mole. So the grams gets cancelled, and you were left with about 4.53 moles of hydrogen. And then you want to find the mole of oxygen, which give you 54.50 grams divided by 16 grams per mole, and this is actually about 3.41 moles, I believe. Yeah, that's 3.41 moles. So after finding that, that is each mole of the element. So after you're finding each mole of your element, what you're gonna do, step number 3, is take the smallest number of mole and then divide all moles. So we have 3.41, 4.53, and 3.41. What's next is identifying the smallest mole, and we know the smallest mole is actually 3.41. So we will take that 3.41 and divide everything. So for carbon, and that is basically 3.41 mole divided by 3.41 mole, and that is equals to 1. As for hydrogen, you have 4.53 moles divided by 3.41 moles, and this would actually give you about 1.34. And for oxygen, you have 3.41 moles of oxygen divided by 3.41 moles, that is also equal to 1. And as you can see, you have one non-whole number, so you have to find a multiplier for this so that it'll become closer to whole number as much as possible. So let's identify some multipliers that we can use. How about, what if we multiply it by 2? That is actually just about equal to 2.68. If you multiply it by 3, that is equal to 4.02. If you multiply it by 4, that is actually equal to 5. I believe, if I'm not mistaken, about 32 or 62 or something, I'm not sure, but yeah. So the closer whole number you can get is actually 3. So what you want to do is to choose 3 as your multiplier. So after doing that, number 4, use the multiplier. So you do not need to do this. You do not need to do this if everything is whole number. But since you have one non-whole number, then you have to find a multiplier. So after finding that, what you want to do is to multiply the multiplier on everything. So you would get, see, you have 1 times 3, that is equals to 3. Age has 1.34, multiplied by 3, you would have 4.02. And for oxygen, you have 1 times 3, you also get 3. Next, after identifying these, this is basically your smallest possible whole number. So that would give you your empirical formula. So your empirical formula is C3H4O3. So this is the empirical formula for ascorbic acids. So not very difficult, it's just tedious work because it's very repetitive and you don't want to get confused. But in reality, the computation is actually not very difficult. It's quite simple. But I hope if you understand, that's how you find the empirical formula. So let's have a quick review. So first, you want to know the percent composition of each element in your compound. And then assume you have 100% or 100 grams of that specific compound. And that is important because it will quickly give you the grams of each individual atom in your compound by just taking the percent composition and making it grams. And what you want to do next, after identifying each grams of your element, is to find how many moles of each element you have by taking the atomic weight, or basically the molar mass of your specific element. Again, you can find this at the bottom number of the periodic table of the elements, and take that grams from our given and divide it by their molar mass, and you would find each individual mole for each element. After taking that, you want to use the smallest mole you found and divide everything. And if everything is whole number, then you have your answer. If there is at least one that is not whole number, then you have to find a multiplier for that whole number, and then you have to use that multiplier and multiply everything to get your empirical formula. I hope that is not confusing. I hope you guys got that, but it's quite easy, really. But if there's any question about this sample problem, do not hesitate to message me. What we're going to do now is we're going to go to our next sample problem. This time, instead of finding the empirical formula, we are going to find the molecular formula of ascorbic acids. Okay, so our discussion earlier centered about finding the empirical formula and then finding the molecular formula. And from our discussion, we mentioned that we can find the molecular formula of a compound if we know its empirical formula, which in this case, we just solve for it. We know that the empirical formula of ascorbic acids is C3H4O3. And what we want next is to know the molar mass of the compound. And we know this molar mass right here. So let's write our given, and then we're going to go ahead and solve for the molecular formula of ascorbic acids. So first, let's write our given. Well, we are given the empirical formula of vitamin C, which is C3H4O3. We were also given the molar mass of vitamin C, which is equal to 176.12 grams per mole. So after identifying that, let's ask ourselves what is being asked of us to find. They asked us to find the molecular formula. Now let's go ahead into our solution. So remember from our discussion earlier, for solution, what we want to do is first find the empirical mass, because this molecular mass right here is not the empirical mass. Empirical mass is the mass of the compound in its simplest form, in its simplest empirical formula. Because molecular mass, we found that by looking for the mass of each individual atom in the molecular formula. I hope you guys remember how to find this. We did that previously on 4.2. That's the molecular mass. But this time what we want is to find the empirical mass. So the mass of the compound in its empirical formula. So how are we going to do that? Well, in order for us to do that, we have to find each individual mass of each element in the empirical formula. So what we're going to do is find empirical mass. In order for us to do that, find the empirical mass, we have to find each individual empirical mass of element. So empirical mass of carbon. In order for us to do that, we're going to take 1 mole of C3H4O3. So we have 1 mole of C3H4O3, and then we are going to divide that to 3 moles, or we have to multiply that to 3 moles of carbon. And we know there's 3 moles of carbon in 1 mole of C3H4O3. I hope you guys remember this. We did this when we were looking for percent composition, I believe. So how did we identify this 3 mole? Well, that's basically the subscript of the C here. So we have C3. That means we have 3 atoms of carbon in 1 atom of, or in 1 molecule of C3H4O3. That means there's 3 moles of carbon in 1 mole of C3H4O3. So this is where we got this. And then we can cancel this right here. And then what we're going to do is to multiply this to 12.01. Sorry about that. 12.01 grams per 1 mole of C. So where did we get this? This is again the atomic weight. This is the bottom number that is found on the periodic table. And we know that in 12.01 grams of carbon, there is 1 mole of carbon. And then we just cancel the moles of carbon. So you're basically left with 3 multiplied by 12.01. And that would give you the empirical mass of carbon. That is equal to 36.03 grams. So that's how you find the empirical mass of each individual element. And we're going to do that for hydrogen and oxygen as well. Let's go ahead and do that. So empirical mass of hydrogen. Again, you want to take 1 mole of C3H4O3 multiplied to 4 moles of hydrogen, and there is about 4 moles of hydrogen in 1 mole of C3H4O3. So this gets cancelled, and remember the atomic number of hydrogen, there is 1.008 grams per 1 mole of hydrogen. 1 mole gets cancelled, so that basically leaves you with 4 times 1.008, and that is actually equal to 4.032 grams. And then next, you want to find the empirical mass of oxygen. Again, so 1 mole of C3H4O3 multiplied by 16, so there's 3 moles of oxygen in 1 mole of C3H4O3. This gets cancelled, multiplied by 16 grams of oxygen per 1 mole of oxygen. So oxygen gets cancelled. You are left with 3 times 16, which is equal to 40 grams. Okay, so that we find individual empirical mass of each element, you want to find the empirical mass of your compound. Empirical mass of C3H4O3. What you just want to do is take each individual grams of your compound. So that is equals to 36.03 grams plus 4.032 grams plus 48 grams. So the empirical mass of C3H4O3 is about 88.062 grams. So per empirical unit. So after finding the empirical mass of your compound, what you want to do next is to find the multiplier. How do we find the multiplier? You have to take the molecular mass of your compound, basically the ascorbic acid, and you want to take this and divide it by the empirical mass. So for number 2, what you want to do is take 176.12 grams per mole and divide that by 88.062 grams per empirical unit. So this gets cancelled, and you are left with this is actually about 2.00 empirical unit per mole. So this is now your X. This is your multiplier. So after finding this multiplier, what you want to do is to multiply this multiplier to each subscript of your element. So for number 3, you have C3H4O3. So C, basically 3 times 2 is equals to 6. H has 4 times 2, that would give you 8. And oxygen has 3 times 2, and that would give you 6. Therefore, the answer to the molecular formula of vitamin C is C6H8O6. So that is your answer right there. This is the molecular formula for vitamin C. Okay, I hope it's clear, guys. I hope you didn't get confused. Again, it's the only thing that probably that would confuse you is this part right here. But yeah, if you guys got confused, just ask me. You can message me anytime so I can explain it clearly. But that is how you find the molecular formula for any compound. And again, if you guys have any question, do not hesitate to message me. And may you guys have a great day. Thank you.